you all for coming. So here we're today here to listen to Vicente's public talk before his defense later on. And so for those of you who don't know, Vicente joined our department in 2010 after he graduated from the National University of Mexico. And there, as an undergraduate, he excelled at physics and computer science. But it wasn't too surprising when he chose to do astrophysics for his vocation, because his parents were influential in the Mexican observational community for many years. So I had a chance to meet his father a few years before Vicente showed up here. And so I was naturally curious to know what Vicente wanted to do with his research when he showed up at the CFA. And so I remember one of the first meetings I had with him, I asked him, would he like to follow in his parents' footsteps? And I got an immediate negative reaction. And, he said he hated observational work, he wanted to have nothing to do with it, partly because I think he said he didn't like dealing with data. So it was ironic to me when he chose the particular topic that he's working on now, because basically that's all he's doing is dealing with data. But of course, this is generated on a computer, not in reality, so maybe that makes it okay for him. At least I never heard him express any regrets about his choices. But he's written a really elegant thesis about how galaxies grow in time using computer simulations. And as part of that, he's been studying how galaxies acquire mass through mergers with other galaxies, which we think is a very important ingredient in how galaxies grow in time. And he's had to develop new tools to do the analysis that were better than anything that's been used before. And he's gotten results that disagreed oftentimes with previous estimates of how these things happen. And one of the things I really admire about Vicente is that when he finds contradictions with earlier results, he tries to understand exactly why they're happening and justify his results very carefully, which is often not done in this community. And so next year he'll be joining Jen Lotz at the Space Telescope Institute for a postdoc. And so today we're here to hear about his work on galaxy mergers with computer simulations.
Okay, thanks Lars for that nice introduction. I will try to be more open about observational data during my postdoc, I hope. Okay, yes, so I'm here to tell you about my thesis work about galaxy mergers and some consequences in cosmological simulations. But first, I didn't turn this on. Yeah, some acknowledgments. First of all, to Lars, my advisor. For providing me with support all these years, and resources, and I don't know. I think he's very good at somehow keeping a very friendly environment in our group, and I think that helps us enjoy graduate school more. Well, to my thesis advisory committee, especially Daniel Einstein, Charlie Conroy, and Avi Loeb, for providing me excellent advice during our meetings. Well, of course, almost goes without mentioning. No, I wouldn't be here without my family, my former teachers, and old friends. So these are essentially the initial conditions when I arrived here almost 6 years ago. My mentors, who I think, well, all of them but one have been postdocs here at the CFA, Annalisa Pilepik, Laura Saldes, Shai Genel, Mark Vogelsberger, Deborah Sujaki, and Chung Pi Ma. Also in a related category, former students who also have been mentors to a large extent, especially Cortina Besla, Diego Muñoz, Laura Bleke, Greg Snyder, who will be my collaborator in my postdoc at Space Telescope, Paul Torrey, Wenfei, and Dylan. Well, current students, they are just too many to list, so I will not even try. But they have helped making grad school much more enjoyable. Other CFA colleagues and the extended Hercules group, which includes people from MIT and that I get paid, which is also important. And well, to my non-astronomers friends, they they exist. They're not imaginary. Germany, in particular. Well, behind the scenes, of course, Peg, Rob Scholten, Nina Sonnenberg, Lisa Catella, they do an excellent job of running this place and taking care of my, just in case you were wondering why I have been carrying this monstrosity of a laptop around for the last 5.5 years. Well, there you go. And it's good for mental health during grad school. And finally, to my official sponsor, Toshiba. Okay, so let's get to it. I will start with some introduction about why galaxy mergers are important and the simulations that I used to study them. This was a key part of my of grad school for me. And then just a few words about how to identify mergers using merger trees. But there's very little science since that. Then I will tell you about my work on merger trees, how to construct them. Then Sourcing Merger Trees was this workshop in the UK about comparing different merger tree algorithms. So I think that's so. Of course, then we go to the applications, which are the three main applications: are the galaxy-galaxy merger rate, stellar mass assembly, which is a term we use to describe how galaxies grow in mass through merging. And finally, I will tell you about the impact of mergers on galaxy morphology, which is a topic of great consequences. Okay, so as you all know, our galaxy, the Milky Way, is just one of many galaxies in the universe. As you can see in this Hubble Ultra Deep Field image. So the first thing you notice is that galaxies look very different from each other. They have different shapes, different colors, different sizes, which is quite remarkable given that the laws of physics are the same everywhere. So if you have a dark matter halo, how do you know what type of galaxy is going to form in the center? So that's one of the main problems that we try to answer in the field of galaxy formation. So one of the mechanisms, the most important mechanisms that is believed to transform galaxies is our mergers. So yes, all of these galaxies that you see here do merge with each other, and this has visible consequences in their shapes and other properties. So I will show you a little. Okay, so this is this is a movie of a very classical merger simulation between two disk galaxies. And as you can see, every once in a while, the simulation is superimposed with a real observed image from the Hubble Space Telescope of interacting galaxies. And you can see a very striking resemblance every time this happens. So I take this as very convincing evidence that mergers do happen in the universe, and they explain many of these features that we observe. So, so this looks similar to the antenna galaxy. I think there was the last one. Okay, yeah, that's about it. Okay, great, I cannot close that. Okay, so so as I showed, galaxies mergers have clear effects in galaxies in the universe. So and they transform galaxies at the center into the supermassive, and they can feed gas in shells. On the left, you have a roughly 1-to-1 merger, which is the antennae galaxies. Okay, so hopefully I convinced you that galaxy mergers are a crucial ingredient in galaxy formation models. And much of our understanding about galaxy mergers comes from idealized simulations. So essentially, simulations of mergers where the two galaxies are set to a collision course from the beginning. So here I'm showing one of these early simulations in which, which was, I guess, the purpose was to test the merger hypothesis to see whether two of these galaxies can produce an elliptical. This was a collisionless simulation, so only dark matter. I mean only particles, stellar particles, and dark matter halo. And you can see that although the end result, the remnant is indeed a mess, it doesn't quite resemble it doesn't reproduce all of the properties of ellipticals. So in particular, this is too diffuse to be compared with real ellipticals. So after these merger simulations have improved by including gas physics, star formation, supermassive black holes, supernova feedback, etc. So it's a very big industry, and I would say that actually idealized merger simulations have reached a decent level of maturity. However, when you try to put these merger simulations into a cosmological context, so essentially having a realistic distribution of the initial conditions for the orbits, mass ratios, gas fractions, all of these details, I think there is a lot of room for improvement. So that mergers are not treated in a systematic enough fashion. Sometimes I even have the impression that mergers are invoked as a sort of as a magical mechanism to explain many properties, many trends that usually sometimes don't fit data well. So I want to put an end to this. So in particular, there is no precise determination of the galaxy-galaxy merger rate. Even simple qualitative statements like whether it increases with redshift, so was it higher at earlier times or not? Even things like these are subject to some debate in the literature. Of course, if you cannot measure the merger rate, then you can also not say statistical statements about their impact on galaxy growth and galaxy morphology. So this is also a topic of debate. Of course, the ideal tool to address all of these issues and more is hydrodynamic cosmological simulation. So I guess most of you can probably guess with which simulation I have been using all this time. Of course, it's none other than the almighty Illustris simulation, where of course the CFA has played an important role. But it's a very big collaboration between Harvard and MIT, Heidelberg, the HITS Institute in Germany. So it's Illustris is a suite of cosmological hydrodynamic simulations on a periodic cube of about more than 100 megaparsecs per side. For the non-astronomers here, this is more than 300 million light years across. There are many versions of these simulations, in particular carried out with different resolutions, so different number of particles. And the highest resolution one has 1820 cubed dark matter particles and another 1820 cubed, approximately 1820 cubed baryonic particles, so stellar particles or gas cells. So for a total of 12 billion resolution elements. So that's for a model that actually attempts to predict galaxy formation from first principles, that's a big improvement over what had been done before. So Illustris had a simple goal, but a very ambitious one, which is to create realistic galaxy populations. And I think it has been relatively successful in doing that. And the physical model that was implemented has been shown to reproduce several key observables, such as the stellar mass function, the stellar mass to halo mass relationship, the cosmic star formation rate, etc., as well as several observables that the model was not tuned for. For example, the appearance of massive compact galaxies around redshift 2, the the appearance of galactic conformity, as we heard about last week, and many other things. So this is perhaps my favorite image, single image made from Illustris here. So this is again the Hubble ultra deep field, but one side is the simulation, the other side is the observations, and you cannot. It's not trivial to tell which is the simulation, which is the observation. I guess many of you already know the answer. So an easy giveaway is that the real image contains diffraction from stars, as you can see here. So yeah, it's not so easy to fool observers with this one. It was even worse a few months ago when I gave a seminar at Tufts University. So they are specialists in galaxy evolution. They even knew many of the galaxies by name in the Hubble ultra deep field. So so that did not work very well. Okay. So here we have some examples of merging galaxies in Illustris. Again, we are comparing two observations, which you can see in the upper row. So you have some famous galaxies like the Mice to the left, and I think that's the antenna galaxies in the third. Oh no, yes, it is the antenna. Yeah, and below you can see a striking example that looks very much like the antenna galaxies. And this all happened naturally in Illustris, which is nice. You can also see some examples of shells, stellar halos showing shells in Illustris. In the upper left, you have the real observations, and in the other panels, you have the mock images from Illustris. And just one more movie here. Well, let's see if it works. Oh yes. Okay, so here we're looking at a region of the universe of 1 megaparsec in length, or slightly more than 3 million light years across. On the left side, you can see the distribution of luminous matter. On the right, you can see the gas density. So this movie is going to show a merger between several galaxies, around 5 or so. The galaxies initially have a disk-like morphology, as you can see in the left. And then in the end, as a result of this merging process, we will end up with an elliptical galaxy, a so-called red and dead elliptical, because it doesn't have any more star formation, no gas. So maybe you sometimes see some explosions on the right-hand panel, which so this is our AGN feedback model, which is currently, I think, subject to some updates. So I think I can. Yeah. Okay. So see, as you can see, on the left hand, you have something in the center that is starting to resemble a real elliptical galaxy. And also the gas content in the central galaxy is becoming very low, so there is almost no gas there, except for the gas that is infalling from other galaxies. Okay, so this is a good demonstration that mergers might be doing the right thing in Illustris. Okay, so that was a huge explosion there. Okay. Okay, so now I will tell you something about the actual work that I did. So this part might be a bit technical, but I think it should be relatively easy to follow. So first of all, the simulation will produce a series of snapshots. So this is basically just the information of the individual resolution elements in the simulation. So you have the positions, velocities, masses, temperatures, etc. of gas cells, stellar particles, dark matter, bulk particles. But if you are just giving all of this raw information by itself, I mean, you cannot do much with it. So there are several important post-processing steps that have to be done. The first one is to run a so-called halo finder. So this identifies, the halos, which are the large virialized structures, so structures in virial equilibrium in the universe. And also, as a result of merging between halos, you get this substructure, as you can see in the upper left panel. So these are called subhalos once the halo enters a larger halo. So the subfine algorithm identifies the central subhalo, which is almost by definition larger than the other ones, and the satellite subhalos. So these are all gravitationally bound structures. And then the particles which are not gravitationally bound are just called FOSS. They are not considered any further. So once you have done this for every snapshot of the simulation, so we have approximately exactly 136 snapshots in Illustris between redshifts of 46 and 0. Once you do this for each snapshot, the next step is to connect these objects across cosmic time. So that is what I do with a merger tree. So the first step is to identify a descendant for every halo. So here you have some halos with a galaxy in the center. So this is a great volume rendering of Illustris here. So yeah, you just want to match these objects with the ones at the next snapshots. So a typical time spacing between snapshots in Illustris is 150 megayears, but it's variable. So you can choose to track the galaxies themselves, so the baryonic matter, or you can track the dark matter particles. Both are very valid approaches. I actually do both, depending on the purpose. But for now, let's focus just on the dark matter. Okay, so how do you match the halos and subhalos from one snapshot to the next? The first approach you might think of is just to look at the positions of this object and then pick objects that have similar positions in the next snapshot. I mean, that's reasonable, except that it's actually not a great approximation because the time spacing is very wide. So many things can happen in 150 megayears, and especially when you have interactions going on. So that's actually a terrible approach. So the good news is that every particle and every resolution element in the simulation has a unique ID. So you can use this information. You just match the IDs from one snapshot to the next. So let's focus on this object on the left. So of course, all of the particles that belong to it will not end up in the same subhalo. They will be distributed across many subhalos, and you just have to pick the right one. So in this case, it's very clear. You just pick. Well, it's very clear that this is the correct one. You just pick the one that has the most common particles. So this will essentially correspond to maximizing a merit function, which is equal to the number of common particles. So that's very simple. So in practice, this also turns out to be not the best approach, because what we find in simulations is that actually the central regions of subhalos are the ones that survive the longest across cosmic time, even when you have interactions going on. So it will be better to put more weight in the central regions of the subhalos somehow. So this is what we do in practice. So this is this is the merit function that I use. Here, the summation is carried out for all particles, for all the common particles. R is the binding energy rank of the particles. So essentially, if you rank particles by how tightly bound they are, the subhalo, and this is just 1, 2, 3, 4, 5, etc. And the alpha parameter controls how strongly you weight these innermost regions of the subhalos. So if you choose alpha equals 0, then you recover this naive merit function. I tried several values, and I think that alpha equals 1 is the one that works best in most situations. Also, alpha equals 1 has a nice property that this will be approximately the natural logarithm of the number of particles in the subhalos, and astronomers love logarithms, so I think that's the way to go. But that's a secondary reason. I also in some situations, the halo finder is not perfect. So sometimes, maybe when a small subhalo is passing through a larger and denser structure, it can disappear. It is lost for temporarily lost. So in order to account for these situations, we search for a descendant both in the immediate next snapshot and also in the next one. And then we compare the skipped descendant with the descendant of the descendant. And if they are not the same, then it means something went wrong, and we take the skipped descendant as the correct one. So this actually helps in many situations. Okay, so once you have determined the descendants of all the subhalos, of all snapshots, you can create what is known as a merger tree. So here I'm showing a nice example from old simulations. You can ignore the colors for now and the different symbols. What matters here is that time goes in this direction to the top, and whenever two branches merge, you have a merger. It's very simple. So yes, knowing the descendants is the main part of the information, but there's something else you need, which is how to define the main branch of the merger tree. So in this case, the main branch is the one on the left, and when two objects merge into a single one, you have to decide which is the main and which is the primary and which is the secondary. So initially, you would just pick the most massive one, but this is actually not such a great approximation, because when you have a major merger where the two objects are comparable mass, so a one-to-one merger, which of the two is more massive is very much subject to noise. So in order to avoid this, we follow De Lucia and define the main progenitor as the one with the not with the largest mass, but the one with the most massive history behind it. So essentially adding all of the masses along the main branch. And if you do this, you get more consistent results. So here I'm just showing results from very old simulations where. So this is the mass of a halo as a function of redshift. So time goes to the left, and if you just take the most massive progenitor as the main one, then you can get different results for different simulations, which are modeling the same object. And if you take this other definition, you get consistent results. So this is important if you want to look at the mass histories of galaxies. Then all of this information is arranged into a merger tree. It is stored in a depth first fashion. So this makes retrieval of information more very quick. In particular, when you want the mass history of an object or the mass histories of objects that merged into an object. So this is what we store. And of course, I try to be a good colleague and make everything easily accessible to my collaborators. So it's all documented and have some examples in my website, etc. And yeah, people have used this merger tree, so that's the good news. Okay, so as I mentioned, I participated in this merger tree comparison project a few years ago. So that was very important because I had just recently passed my research exam. I just had this merger tree algorithm, and there was going to be a workshop about merger trees. So I decided to participate. It was very nice because I saw that my merger tree algorithm was comparable. Yeah, I mean, it did well. It did well in the comparison. So here you can see different kinds of algorithms. I won't go into detail, but Okay, so these are the ones that use particle IDs to identify, to track the descendants. There's one outlier which used only positions, as I mentioned, which it didn't do very well. It's the cyan line here. It was a bit of an experiment, so just to see what happens. And here you can see that actually different merger tree algorithms can lead to very different results. In particular, when you look at the abundance of satellites above a certain mass. In this project, in this workshop, they also looked at pathological situations which create problems for merger trees. So here, for example, you can see, okay, so you identify two subhalos at redshift 0, which is the right column. Okay, so you have a large blue subhalo and a small red one, and you try to track them back in time. Here you see results from different merger tree algorithms. So in the upper one, you can see that the blue subhalo is lost after just a couple of snapshots, and there is only a huge red subhalo. The one in the middle row, which is the one that they used at the Durham. Oh, I just realized that's why it's called Durham tree. I haven't realized that. So this one does better. I mean, it doesn't lose track of the subhalos. But there is a big mass jump here, so red becomes huge, then small again. Finally, what my algorithm did in this case was actually skip the subhalo. So yeah, it's maybe that's better, maybe not. I don't know. So I mean, I never said it was a nice business. You have to deal with all the imperfections of the halo finders, which is the previous stage. And finally, I will just say a few words about how to actually detect mergers using merger trees. As I mentioned, this happens when two branches of the merger tree merge with each other. So here I'm showing the mass history of two galaxies that merge with each other. The blue is the primary object, the red is the secondary. And this is a 1-to-1 merger, 1-to-2 merger, and 1-to-4 merger. So these are all major mergers. As you can see, the secondary increases in stellar mass even after infalling into the halo of its new host. It can still form stars after infalling. Then it reaches a maximum and then it drops. And this decrease in mass is a result of stripping, both physical stripping, and also there's usually a bit of a numerical effect as well. So in any case, you want to avoid taking the mass ratio right before the mergers. So a much better approach is to take it at the moment when the secondary reaches its maximum mass. So for example, this is a 1-to-1 merger because that's the mass ratio when the secondary reaches the maximum. If you had measured the mass ratio right before the merger, this would be like 1-to-20 or something. So it would not count as a major merger. So this actually happened to be a key aspect of my merger rate determination. So it gives much more robust mass ratios and therefore much more robust measure rates. Okay, so that was the technical part. Now I will actually show some science. So these are the three main applications of my merger trees. The first one was about galaxy merger rates. So the motivation for this is that the galaxy merger rate is very poorly constrained. As you can see here, this is a plot of the major merger rate. So essentially how many major mergers a galaxy undergoes in a gigayear as a function of redshift for different masses. These are small galaxies, medium, larger galaxies. The color lines are showing different predictions from semi-analytic models. Well, from semi-analytic models and one hydrodynamic simulation, which is the yellow line here. And you can see there is a very large scatter of about an order of magnitude. And the error bars are showing observations, but there's also a caveat with the observations, which is that observers cannot measure the merger rate directly. They can only observe the merger fraction and then convert to merger rate by assuming some time scale. So you should also take the observations with a grain of salt here. And finally, the black lines. The black lines are so-called semi-empirical models, such as abundance matching, HOD models, and things like that. So these models are different because they do not they don't attempt to model galaxy formation from first principles. Instead, they just consider a dark matter only simulation, which is, in a technical sense, it's easier to carry out. Then just populate the halos with galaxies. So essentially just paint galaxies onto the halos according to observational constraints. So this way, they can eliminate much of the complexity in galaxy formation. And yes, so the black lines are in reasonable agreement with each other. On the other hand, these models also make several assumptions. For example, that every merger between two halos leads to a merger between the central galaxies. And so it's also it's ideal to do this with a fully self-consistent hydrodynamic simulation, which is what I do. On the other hand, the merger rate of halos, of dark matter halos, so not of galaxies, but dark matter halos, is very well constrained. And in fact, it has a very simple mathematical form. So here I'm showing results from Fakuri and Ma in a very important paper in this, in 2008. So here you have the merger rate, the number of mergers per unit volume, per unit mass, per unit redshift, per unit mass ratio as a function of mass. Yes, I know. But what you take away from here is that it's a power law with respect to the mass ratio of the merger. And of course, since you have more, smaller galaxies are more numerous, you also have more mergers. So you have a higher merger rate. So what they found in 2008, so this is from a later paper, but what they found in 2008 is that if you divide this merger rate by the number density of galaxies, then they all overlap in essentially the same line. So they call this a semi-universal relationship, almost universal merger rate of halos. And indeed, it has a very weak mass dependence. So I was very impressed by these results. I think it's a very nice result. So the goal was to do something similar, but for galaxies. And of course, with the Illustris simulation just recently finished, it was a great opportunity to do this. And what do we find? Well, we find that indeed the galaxy merger rate also has a relatively simple mass dependence. Mathematical form. So here I'm showing the merger rates. So the number of mergers per galaxy, per unit mass ratio, per unit time, or per gigayear, as a function of mass ratio. And it's also a power law. The dotted lines show a fit, a fit that I found to the data. Now, if you observe very closely, you'll see that the lines are not exactly parallel to each other. So there is a bit of more complexity when you look at galaxies, but qualitatively it's not so different. As a function of mass, I found that more massive galaxies are somewhat more likely to have mergers. So in this case, I'm showing the cumulative merger rates. So, the number of mergers with mass ratio greater than what is shown here. So for example, the blue line is the major merger rate of galaxies as a function of mass. This kind of plot can be useful. For example, if you consider, a Milky Way-like galaxy at redshift 0. So that's mass somewhere over here. Its merger rate is 1 in 50. So essentially, on average, 1 in 50 Milky Ways undergoes a major merger in the last gigayear. And of course, I determined this for every redshift, every mass ratio. So it's a very general measurement. And finally, as a function of redshift, I found a very strong redshift dependence. So the merger rate was much higher at earlier times. So I think this will finally hopefully settle that actually the merger rate increases with redshift. So this has been debated both from observational and the theoretical side. Finally, I compared to some observations. Consider the caveat that I mentioned that they cannot really measure these things. But our results are consistent with observational constraints. So this is the most credible determination of the merger rate from observations, which is by Jennifer Lutz. So they compiled observations by different authors and estimated the corresponding merger timescales as accurately as they could, and this is the constraint that they came up with. And results from Illustris go right through the middle of that. So here I'm showing different Illustris simulations, Illustris 1, Illustris 2, Illustris 3. So these are different resolutions of the simulation. You can see that they are in excellent convergence. So essentially, I get the same merger rate when I have 8 times less particles and 64 times less particles. So that's good. And this is the same, but just for a more massive mass range, for larger, higher mass range. Here I have to compile the observations manually. You can see that some of them actually predict a flat or even decreasing redshift dependence. So I think this is quite interesting. Actually, right now, currently, I'm working a bit with Greg Snyder and Jennifer Lutz on actually measuring the timescales, the observability timescales that can be used to convert these observations into a merger rate more precisely. So this is all good. However, there is as Lars mentioned, there is huge disagreement with some earlier theoretical predictions of the merger rate. So on the left, you can see what is perhaps the best known attempt at measuring the galaxy merger rate. Before this is by Wu and White using a semi-analytic model of galaxy formation. And they found very strong mass dependence. So these lines are the merger rates for galaxies of different masses. They're very different. So large mass dependence and very weak redshift dependence. Of course, the units here are a bit different. So it's not per gigayear. It's per Hubble time or something. But if I convert to the units that they used, I still get something qualitatively very different. So I get a weaker mass dependence and a stronger redshift dependence. So completely the opposite. Okay, so that was the merger rate. Now, the second thing I did was to measure what is at the end of the day, what are the consequences of mergers for the galaxy growth? So how much of a galaxy's mass was acquired through mergers? How much was formed in situ, etc. So this paper might be more interesting to some. Of course, the motivation is that, as I have mentioned many times, there is no consensus regarding how much of a galaxy's mass was acquired through mergers, and this can be quantified with the ex situ stellar mass fraction. Where ex situ is essentially ex situ stars are stars that formed in other galaxies which were subsequently accreted. On the contrary, in situ stars are stars that formed by star formation in the same galaxy where they are currently found. So we investigate the origin of stellar particles individually. So for each stellar particle in the simulation, we check whether was it formed in the same galaxy where it's currently found or in another galaxy. And things like that. So this is taking things another level, a level above what we did for the merger rate. So this is what we get: the ex situ stellar mass fraction as a function of stellar mass. You can see that it's a very strong function of stellar mass. So for Milky Way-sized galaxies, approximately, it's around 10%. And actually, for the Milky Way, it's probably even lower because the Milky Way is known to have a relatively passive merging history. For the Milky Way, it's about, we think it's about 7% based on a different set of simulations. But on average, it's more like 10% or not to 20%, depending on which region of the universe you happen to live in and things like that. But then for massive galaxies, this can increase quite rapidly, even to 80% or more for the most massive galaxies. So this means that very massive galaxies start to grow primarily by mergers. Now the error bars here are showing previous theoretical studies. So there are no observations here because this cannot be measured directly. But yeah, also previous theoretical predictions predicted a very large scatter. And it seems that our prediction goes through the middle of all of them. So it's almost like the median of all the other studies. And again, I'm showing a resolution study here. Illustris 1, Illustris 2, Illustris 3 are the solid dashed dotted lines. So the results are well converged. So that's always good to check. Now, out of the stars that were acquired through mergers, that were ex situ, we also determined how much of it was from major mergers, how much from minor mergers, and so on. So if you define major mergers as usual, so essentially mergers where the mass ratio is 1 to 4 or larger, we find that on average, it's just on average, not the median. Unfortunately, this also matters in this case. So on average, about half of the mass, stellar mass, of the accreted mass comes from major mergers. About 20% from minor mergers, which is from 110 to 1/4 in mass ratio. Then approximately another 20% from very minor mergers, which is all other mergers. And then there is a non-negligible contribution of about 10% of stars that were stripped from surviving galaxies. So this can be an ongoing mergers or flyby, things like that. And what I find most remarkable of this is that it's approximately mass independent. Yeah, you can go. This is a consequence of also the galaxy merger rate being almost universal, and a power law as function of mass ratio. So this is one of the key plots in the paper, which shows that some previous theoretical models have proposed that essentially all galaxies, even of the size of the Milky Way and larger, form through two different phases. So there is an early stage of in situ star formation where a galaxy accretes gas and then forms in situ stars, and then a later stage where it grows through dry mergers. So there's a few famous papers which claim that most galaxies grow in this way. On the other hand, there are papers based on different techniques like abundance matching, which show that actually the ex situ contribution to growth is actually less than half for all masses. So we do this with Illustris, and we find something in between, which is that for massive galaxies do grow in this two-phase manner, but for less massive galaxies, most of the stars were formed in situ, which is this red line. So time goes to the left, as always. So finally, since we have information about the origin of individual stars, we can also visualize this. So here I'm providing a visual impression of galaxies and their stellar halos. The upper row is a small galaxy of about 10 to the 10 solar masses. Then there is a 10 to the 11 solar mass galaxy. And this is a 10 to the 12 solar mass galaxy. The columns show, on the left you have all the stars, including satellites. And then you have all the stars without the satellites, as determined by our halo finder. Then you have all of the ex situ stars, and then all of the in situ stars. So as you can see, the in situ stars are found very close to the center, which makes sense because that's where they form. On the other hand, ex situ stars are found all around the galaxy, and they can even show stellar halo features such as tidal streams and shells. So now, in a more quantitative sense, we have measured the cumulative mass profiles of the different components from in situ stars, major mergers, minor mergers, etc. And what we find quite consistently is that, well, of course, in situ stars are found the closest to the center, but then among the accreted stars, the ones that were accreted in major mergers are ultimately found closer to the center, and followed by minor mergers, very minor mergers, and finally stars that were stripped from surviving galaxies. So this is consistent with predictions from older n-body simulations of idealized mergers. And finally, the last application is, how do mergers affect galaxy morphology along with halo spin? So in the simplest possible scenario, the morphology of a galaxy. So the the factors that determine if it's a disk or a spheroid are believed to be how quickly spinning its halo is, and also the emerging history of its halo. So that in the simplest possible case, disk-like galaxies form in quickly rotating halos with passive merging histories. Spheroidal galaxies form in more slowly rotating halos with violent merging histories. So no, we want to test this using the Illustris simulation and using the merger analysis tools that I have developed. So first of all, I can show that actually there are disks and spheroids do appear in Illustris naturally over a wide range of masses. So here we have disk galaxies and spheroidals. So this is from 10 to the 9 solar masses to 10 to the 11. Well, 10 to the 12. I'm not showing 10 to the 12, but we also have that. So that's 3 orders of magnitude of reasonably resolved morphologies. And for each of them, we have all this information about merging histories, the spin of their halos, etc. So, so halo spin, this is measured, this is like an a-dimensional and mass-independent measure of its angular momentum. So we use this definition by Bullock, according to which the spin of the spin parameter of halos can be described by a log normal. So this is just a consequence of the tidal torques in the early universe, and it's a simple way of quantifying the halo spin. The other factor is the emerging history, and this is what has not actually quite been done before in any study that I know of. So we quantify emerging history. I guess to first order, we use simply the ex situ stellar mass fraction. So this can tell you roughly if the galaxy had a violent merging history or not. But also, you have to keep in mind that massive galaxies are more likely to have dry mergers, so gas-poor mergers. Less massive galaxies are more likely to have gas-rich mergers. So there's more information that you have to keep in mind. But to a first approximation, the ex situ stellar mass fraction is positively correlated with gas fraction, look-back time, and mass ratio. So this means that it's a good proxy for, what did I say this here? Recent, dry, and major merging history, which is the kind of merging history that is believed to form spheroids. So this is what we use. And what happens if we combine all of this into a single plot? It's the last plot. That's the good news. So here on the, I think it's the last plot. So here on the y-axis we have the ex situ stellar mass fraction. So this is quantifying the merging history. On the x-axis you have the halo spin. So it quantifies how quickly rotating the halo is. And the color is a measure of morphology. In this case, it's the fraction of kinetic energy invested into ordered rotation. And what you can see in most panels is that there is a sort of a diagonal color gradient, so that, this agrees with expectations. Galaxies that are found in slowly rotating halos, which have high ex situ fractions, tend to be spheroids. And galaxies in more quickly rotating halos with passive merging histories tend to be disks. So that's the general case. However, there is something a bit surprising, is that there is a mass dependence here. So as you reach higher masses, the gradient becomes vertical, which means that in this case morphology is determined by merging history alone, and not so much by halo fraction. So essentially, the mergers are erasing any possible pre-existing trend that you had from the halo spin. And then at lower masses, the gradient seems to become more horizontal, so that even when you have major mergers, the galaxy can reform a disk around it, and its morphology is correlated with the halo spin of its dark matter halo. So this is a nice result. I think it will appear in the archive pretty soon, I think. So I mentioned. So this idea is not new, that if you have a gas-rich merger between two disk galaxies and the result is also a disk, it seems to contradict the merger hypothesis, but it's not completely new. It has been found by some simulations, idealized merger simulations. However, something that got me pretty excited about a week ago is that Martin Sparr, who is visiting right now, resimulated mergers from the Illustris simulation. So here the difference with respect to previous studies is that these are in a cosmological context. So they are not galaxies set in a collision course from the beginning. It's a cosmological context. So I will just show you the last over here. Yeah. Okay, so here you have, okay, on the left you just have this temperature density diagram, which is used to classify, to distinguish hot gas from ISM and star-forming gas or cold gas. The image in the middle is like a composite of these three colors. So that red is just hot gas, yellow is a combination of hot gas and ISM, and white is a combination of the three colors. So white is where you find the star-forming gas, and on the right you just have how the galaxy would look like. And what you can see here is okay, you have a merger between 5 objects approximately. And in the galaxy becomes red and dead for a moment, but then starts to accrete more gas, and in the end forms a disk around it, as you can see here. So this is in agreement with what I found. I think what I found in Illustris as a whole gives some statistical support to these zoom-in simulations. Okay, so I will leave you with my conclusions. Yeah, thank you very much. Yeah.
Questions for Vicente? Nobody?
Yeah, so I have a question. A lot of you showed the idea that tracing mergers in different ways, like, gives you different merger histories. And one thing that struck me was the idea that you have whenever there's a merger, there's the primary galaxy or the primary in the merger and the secondary member of the merger. And you showed the different ways of counting which is the primary, which is the secondary, leads to different sort of histories of how galaxies develop. Is there a definition which is some sort of like principled definition that you're trying to match? Or is it more like an ad hoc definition? Essentially, it's like, is there a way to say, like, there is some sort of idea that we're trying to match that when we make these definitions, and one idea makes more sense than the other?
Okay, so you mean when I define the who is the main progenitor of a galaxy?
Yeah,
what is the ideal behind it? I guess really you just want to. I mean, if you have a galaxy and you look at its main branch, you just want to be able to say that it's the same galaxy in some way. So I mean, this is just the most robust definition I found to do this. To be able to say, okay, this is the galaxy at a redshift 2 or a redshift 3. If I take the other definitions, I can get it's subject to noise, and it's just not robust. So it's more robust than the other ones. I'm not trying to match anything in particular.
In the end, you're trying to match these to the observations in some way. And I was wondering if there's like different.
Oh no, but it's the other way around. I think the observers are trying to match the theory because observers cannot say, okay, so these galaxies evolve into these other ones, right? So they have to rely on our predictions to be able to make statements about how galaxies evolve into one another. So yeah, I don't think there is an observational analog that I'm trying to match. Yeah.
So with the gold and white paper, what was going on there?
Oh yeah, well there are many reasons. So of course, I mean, first of all, merger rate is kind of a derived quantity, so it's instantaneous. So it's very sensitive to different definitions. But I think in this case, I think actually the treatment of satellites actually helps. Well, I mean, it has been shown that different ways of treating satellites can lead to large differences in their properties. So, for example, once there is a merger between two halos, the satellite galaxy, almost by definition, it cannot accrete any more gas, so it quenches very quickly. And I think that has a lot to do with why they find smaller merger rates. So essentially, their satellite masses are much smaller than what they should be. On the other hand, in Illustris, as you know, we find that actually satellites can even continue to form stars after inflow. So I think it's something along those lines.
Just to clarify, in the semi-empirical models, they quench by definition after.
Oh, so in this,
Sorry, in the semi-analytic.
yeah, in the semi-analytic models, they quench by definition after inflow. You mean?
Yeah.
I think so. Well, I mean, right. Depends on which model. Yeah.
Different semi-analytic models give very different results for merger rates as well as we saw in the
Yeah.
Vicente, in your pathological merger example, in the second to the last snapshot where you can only see one merger rather than two, is it just because they're superimposed? And then in that case, you can use the velocity structure to actually identify two different subhalos superimposed.
Yeah. Well. First of all, I mean, it's really a problem with the halo finder. So because as you can see here, you actually have a one-to-one. Well, it's a major merger. I'm not sure if you can see here, but the two nuclei in the central region of the halo, they have the same size, right? Pretty much. So why should one of the subhalos be much larger than the other one, right? So I'm actually blaming the halo finder for this, and then the merger tree algorithms. I mean, we just try to do what we can. Right? So your question was. So yeah. I mean, there are many things. So the density contrast becomes very bad. A phase space halo finder. It will be interesting to see what would have happened with a halo finder that takes into account velocity information, but we did not do that here.
Well, some of them do. Some of them in that sense.
Oh yes, some of them. Yeah. I'm not showing the other second part of the plot, but yeah, some of them actually reconstructed, recreated the halo finder. But that's. I mean, they're playing by different rules. I mean, in that case. Yeah. Okay.
More questions? If not, let's thank Vicente again.
Okay. Thank you. Oh, thanks.
What's the next?
Oh, so
What time are we meeting again?
oh, so we meet. I think it's at 11:30 in the classroom.
Okay. Perfect.
Oh, thanks.
A lot of content.
A lot of what?
A lot of content, and
Oh, okay.
to cover in an hour, and you did. So.
Oh, great. Thanks.
All right, thanks
Hi.
very much. I'm Steve Weltner from across the street.
Oh, okay.
We've never met.
Turn off your mic.
I just had this was a really great presentation.